Warn you at the outset of this video that I'm working in my office, which I share with my bride, and she's here working too, so we're going to get a little bit of background noise every once in a while. I'll try to warn you about that, so hopefully it won't be too distracting. Alright, so chapter 14, section 6. We can figure out the equilibrium constant, which we typically write as Kc. We can figure out the equilibrium constant if we know the concentrations of all the components. Okay, that is all the reactants and products. Okay, if we know the reactants and product concentrations, then we can figure out Kc. Oh, by the way, with this one qualifier, we can figure them out if we know them at equilibrium. Okay, that sounds like a throwaway word for now. Oh, sewing machine, just a moment here. Go ahead. That sounds like a throwaway word right now, but it turns out it's going to matter here in the next section. Okay, so we can figure out the equilibrium constant Kc if we know the concentrations of the components at equilibrium. All right. Now, let me remind you, we got, I think in section 14.3, maybe 14.4, what the equilibrium constant, what the form of the equilibrium constant was. This is called the law of mass action, and the form of it is here, and we're going to use it over and over and over again. Oops, whoa. Sorry. The form of it is here, and we're going to use it over and over again, so I want to just look at it real quickly here. Don't forget that if we have some reaction, A plus B is in equilibrium with C and D, that is A moles of A and B moles of B, right, is going to give you C moles of C and D moles of D. Then we say that the equilibrium constant K is equal to the concentrations of the products over the concentrations of the reactants. And note here, look, this is not a plus. This is a times. This is a multiplication symbol. Okay? This is a times. This is a plus. This is a times. All right? You'll do this often enough. I think you'll eventually get very good at it. But all right, so this is what we're talking about, the law of mass action. And this we saw in a previous section, 14.3, 14.4. All right, so if that's the case, if I told you, of course, what C was, and what D was, and what A was, and what B was, you would just multiply and divide, right? And that's what we're going to do here in this section. We're going to say if we know these, then we can solve for K. All right, so let's go here and look at it. For example, suppose I start out with half a mole. This is a busy table. This is on page 579, maybe? Nope. This is on page 575. Page 575. Okay, suppose I start out with a half a mole of H2, my concentration, or half molar, I should say, right? Half molar H2 and half molar I2, according to this reaction. This is a busy table, so I'm walking through it with you carefully, okay? A half mole and a half mole, or half molar, and 0 of the product, then in the end, I'm going to get some product, right? That's the whole point. You're going to get some product. Well, suppose I told you that the concentration of the product in the end at equilibrium was 0.78, and that left 0.11 and 0.11 of these guys, then the equilibrium constant Kc would be 0.78 squared, right? Because don't forget, the law of mass action says, well, I'm gonna do the equilibrium constant expression for this one. It's going to be Hi squared, right? And the concentration of H2, should be calling these guys by name, right? Iodine and hydrogen and hydroiodic acid. Okay, and that's the expression here for Kc. So that's what we got. 0.78 squared 0.11, 0.1. Let me point something out here. Actually, let me make this a little bit smaller and point something out. Let me go with this first line here and say that this is where we first see our ice table. Okay, so what's an ice table? H2. It's sort of set up right here, okay? And hydroiodic acid, initial concentration, change, and equilibrium. Well, I'm giving you here the equilibrium and the initial. So the initial is 0.5, 0.5, and the initial for iodine is 0.5. Can you see it over here? Right here, right? And the initial for hydroiodic acid is 0, right? And we're told then, according to this table, that the equilibrium is 0.11 and 0.11. And what is it for hydroiodic acid? You see it 0.78. Well, let's look at this. How much was subtracted from this? So some H2 turned into hydroiodic acid, right? How much? Can you see that it's 0.39? So it looks like 0.39 is going to give you 0.11. Right? And how much iodine was consumed? Consumed 0.39. Right? And how much hydroiodic acid was produced? Well, 0.78. You can see 0 to 78, right? Can you see that this 0.78 is double of the 0.39? Look at that. And why is it? Well, it's because we know, and here's what the ice table looks like, and we're going to be doing this for the whole next couple sections. Hydroiodic acid, I'm drawing it out again, but ice, I'm supposing now, as I'm setting this up, I don't know what the equilibrium is. I'm going to go 0.50, 0.50, and 0.00. And here's the magic with the ice table. How much ever I lose from H2, let's say it's X, okay? How much ever I lose of X. Can you see this is 1 to 1? Can you see that from where you're sitting? Is that too small? Let me write it down here. H2 plus I2 is in equilibrium with hydroiodic acid. Can you see that, rather it's two of those, right? Can you see for every mole of H2 that I lose, I'm also going to lose a mole of I2. Okay, so let's suppose I lose X. I'm going to lose X of that. Can you see for every mole of H2 that I lose, I'm going to gain 2 moles of HI, right? I'm losing a mole of H2, or I'm losing X moles of H2, and I'm going to gain 2X of HI because it's a product, right? And that's exactly what I've got up here. Okay. So the same thing goes for these other ones. Let me erase this real quickly here and do another one. So suppose I've got. Let's go with the second row here. With the second row, I'm going to write the reaction again. It's H2. It's hydrogen. Gas plus iodine gas is in equilibrium with hydroiodic acid. It's probably a gas too, yeah, it's a gas, okay? And if that's true, so what I'm going to do when I'm setting my ice tables up is I'm just going to use my balanced reaction here at the top, and I'm going to say I, C, E, right? And I'm going to go to my question stem, and it's going to tell me I've got 0 in the beginning and 0 in the beginning of I2, right? And how much hydroiodic acid do I have? 0.50 molar, right? This is in molars. Okay? Now, if that's the case, how much H2 am I going to have in the end? What's the change going to be? Well, I'm going to have some H2, right? Because this is an equilibrium. So it must be that I'm going to gain some H2. Can you see that? And I'm just saying X because I'm choosing a variable, right? And if I gain X H2, how much I2 am I going to gain? Well, the same, because those are a 1-to-1 ratio, right? Or rather, 1 to 1 to 2. See that? So if I gain an H2, some of it's going to come over here. There's going to be some I2 that comes as well. All right. How much HI am I going to lose? Oh, looks like it's going to be minus 2x. Right? Can you see why? Because this is a 2 to 1 to 1 ratio, right? And I'm losing it because I'm starting with 2 here, and I'm starting with 0.5 here, and 0, right? And you know you're not going to have 0 in the end, so you're going to gain. So since this is gaining, that's going to be losing. All right, that's how an ice table's set up. Now, it turns out we know what, because I chose this row right here, we know what the final concentrations are. The equilibrium concentration is 0.055, right? And that's also 0.055. They're going to be the same because I started with 0, and it's a 1-to-1 ratio. And this goes to, I wouldn't even have to look, really. 0.3, and we can figure it out from here, right? So what is x? You tell me. Pause the video right here and tell me what is x. You can tell by looking at it. Okay, let me suppose you pause the video. X is 0.055, right? 0 plus x is 0.055. Okay, now let's prove it to ourselves that this was useful. 0.05 minus 2x is equal to 0.39. Now, 0.50 minus 2x, I'm assuming this is going to be a true statement, right? If it's not, then our table's wrong. 0.05, this is 0.055, and 2 times 0.055 is 0.11 minus 0.11, and this is true. That means we set it up right. Okay, so look, you don't really need an ice table for this exercise. I'm only showing you how the ice table is set up. Whatever we lose over here, we gain over here. Whatever we gain over here, we lose over there. And sure enough, these numbers show that the x's as we set them up work perfectly. Okay, so we're going to do ice tables more in the next, not the very next section, but the section after that. For now, that's what an ice table looks like, and that's why we set it up, or how we set it up. Okay, I think that we have a practice problem now. Oh, let's do the x table. Let's do the ice table for this. Trove does show you this ice table in this section. This graphic comes from this section. So let's look at this. If our change, can you see that are we losing or gaining here from 0.5 to 0.15? Are we losing or gaining? Can you see that we're losing, right? So I'm going to put minus here, okay? And I'm going to call it x, although we can tell about what x is going to be. And if we lose x here, how much are we going to lose here? 1 to 2, right? This is going to lose 2x. And if we lose x here, are we going to gain or lose? Here, we're going to gain, right? Can you see that? Okay. Now we can tell what x is. Let me encourage you, please consider pausing the video now and solving for x, because we have an equation up here, and you need to think about how these equations work. Okay, let me suppose you paused it. And I'm going to write this out. You know that 0.500 minus x is equal to 0.15. What is x? I can't do that in my head. This implies that 0.500 minus 0.15 is x, which implies that x is equal to 0.35. And that's exactly what it is, okay? So x is 0.35, so how much is lost here? We don't need to do this problem for this section, okay? It's just an example that's given. But I would like you to, fill in these circles here, fill in those 2 circles, and then you will, that'll be another chance for you to practice an ice table. Okay, we'll see why we need it here in a little bit. I think I might have another ice table here. Yeah, I do. Okay, let's do the same thing here. What I got? Okay, so it looks like I'm losing methane. Can you see I've got some methane in the beginning? And I have no C2H2, I guess that's acetylene. I have no acetylene in the end, and so we're going to gain some of that, right? And we have no H2 in the beginning. I'm sorry, in the beginning I have none, but I have some in the end, right? So we're going to gain here, and we're going to lose here, right? Because if this is gaining and this is gaining, this must be losing. Okay. So that said, we're going to call, let me say, that, can you see I have a 1 to 2 to 3 ratio here? So let me call this X. And how much am I going to be gaining over here? 3X. And how much am I going to be losing here? 2X. Okay? So let me ask you, pause the video and write out what those must be. This is a very important part of your understanding an ice table. Okay, so I didn't show you the answers in the last one, but I'm going to show you the answers in this one. I can see that 0 plus x is 0.035. So x must be 0.035, okay? X, 0.035. 2x, I can do this one in my head, 0.070. Okay? And 3x, I can't do that one. Yeah, I can. 0.105. Okay? Plus 0.105. So this goes to 0.105 molar. And this goes to, I can't do that one. What is, I'm running out of space here, okay? So I'm going to cordon off some space. This is 0.115 molar minus 0.070 molar is equal to, I can't do that in my head, just a minute here. Yeah, I can. It's 0.045. 0.045 molar. You know what I'm going to do? Just that's going to be very frustrating for students if I calculate that wrong. You should be calculating this too. 0.115 minus 0.07. Yep, 0.045. Okay, 0.045 molar. 0.045 molar. Right? This is in molars. All right, and this is molar. Okay, so you get that? That's how ice tables are. That's how we manipulate ice tables. We'll see in a minute why we need them desperately. All right. Now, I think we have a practice problem here. Yeah, so find equilibrium constants from experimental concentration measurements. Consider the following reaction. So reaction mixture at 780, blah, 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 initially contains, okay, so initial, I'm going to CO, it's carbon monoxide plus 2 hydrogen gases, gives me methanol, right? Initial change equilibrium. Okay, so the initial is 0.50 of carbon monoxide, 0.500, and of hydrogen it's 1 molar, 0.00. At equilibrium, the concentration is found to be 0.15. Now you can see why I need this, okay? 0.15. So, a reaction mixture initially contains, okay, so it says it contains this and this, but apparently it doesn't contain that. All right? Now, if that's the case, this is just like the one we did on a previous page. If we start out with this and we end up with that, are we losing or gaining? We're losing, right? And if we lose some of this, are we going to lose or gain that? It's on the same side, right? So we're going to lose that, and we're going to gain this. Okay? So let's say that we lose x, because this is a 1. Oops, crud. I got to start this over again. My pen doesn't save this stuff. All right, I'm going to be a little fast here. CO methanol, initial change, equilibrium. Can you read my writing? And this is initially 0 because it says it contains these two, but it doesn't say anything about methanol, so it must be nothing there. It does contain this, though, 0.50. 0.500. That's a 0. I'm going to go a little slower here. 1.00. And at equilibrium, it contains 0.15 molar of that, right? We lose this because you can see it's going from 0.5 to 0.15. We're going to be losing some here too because it's on the same side. And we must be gaining over here because we're starting with 0, right? Okay, or because if we're losing this stuff, it must be going to methanol, right? That's what the reaction means. So let's call this X because this is a 1 to 2 to 1 ratio, so we'll call that X. If this is losing X, what's this losing? 2X. And if this is losing 2X, what's this gaining? X, okay? All right, so we see that 0.500 minus X equals 0.15. 0.500 minus 0.15 is equal to X. X is equal to 0.350. Okay? Now, if X is 0, we just did this in the past slide, the most recent one. 2X is going to be 0.7. No, we didn't do this one. We did something like it. 700. Okay? So 1 minus 2X is equal to 1 minus 0.700, which is equal to 0.30. This only has, if we're subtracting, we can only go up to that point there. 0.30. This one does have an extra 0 in it though. Sig figs issue, right? Okay, and the third one is 0 plus X, and that's easy to do. It's 0.350. 0.350. All right? So what is the value of the equilibrium constant? Aha, okay, the equilibrium constant is going to be, when I'm doing this, I'm going to write this out, CH3O carbon monoxide and hydrogen. It looks like that's squared. Agreed? So this is 0.350 over 0.15 times 0.30 squared. Didn't quite leave myself enough room here. K is equal to, clear 0.35, just a second here, 0.15, 3. You should be calculating this also. Please do not wait for me. It's very easy. Times 0.15. Very easy to sort of zone out. And if you zone out, you don't learn as much. It's not nearly as efficient as focusing. So I'm trying to ask you leading questions. Do your best to pause the video when I recommend that you do, and so on. It just keeps the blood flowing better, and you'll learn so much better. Even it's uncomfortable, but you got to try it. So this goes to be 25.926, and it looks like I've got how many sig figs here? 3 sig figs in that concentration, right? That's got 3. This only has 2 sig figs, and this has 3. So it looks like this is going to be to 2 sig figs, 26. There's our answer. K is equal to 26. Okay, and it looks like I've got one more example problem, and this is turning out a little bit longer than I expected, so let's roll. Okay, consider the following reaction. I'm going to do the same thing here as I did before. I'm going to say 2C, oh wait. 2CH4. Jill, do you need to do more in here?
Mm-hmm. I will in just a few minutes.
Okay. Plus 3H2. I'm crowding this over here to the side so I have a little more room. Okay, so a reaction mixture initially at 1700 means nothing. Initially contains this, okay? If it initially contains 0.115 at equilibrium, okay, so it has nothing in that except that. So this is going to be 0 in the beginning, and this is going to be 0, right? And can you see that this is a 2 to 1 to 3 ratio, right? 2 moles of this, 1 mole of acetylene, 3 moles of hydrogen gas. Okay, at equilibrium, the mixture contains this much acetylene, 0.035. We calculated this in a previous previous slide a few minutes ago in this video. All right, so can you see that this is going to be gaining? Acetylene is going to be gaining, okay? And I'm going to call it X because it's a 1 to 2 to 3 ratio. So if this gains X, what does this gain? 3X. And what does this lose? 2X. Okay? Again, I know we did this in a previous video. So you can see what X is. X is equal to, right? Can you see it from right here? 0.035. 2X. 0.070. And 3X, 0.105, right? Okay, so if that's the case, 0.105, then what do we have here? So 3x, 0 plus 0.105 is 0.105, and I can't do that one in my head. 0.115 minus 0.07. Oh yeah, we did this in a previous slide, didn't we? 0.045, okay? 0.045, okay? And the question is, what is the value of the equilibrium constant? Well, the equilibrium constant, Kc, is going to equal to acetylene raised to the 3, right? And methane squared. Okay, so we very carefully laid this out, so I'm just going to go look numbers up. 0.035 is my writing too small, and H2, 0.105 cubed, and it looks like it's 0.045 squared. Okay, is equal to, all right, so let me calculate this. You should do the same thing. 0.105 cubed. Times 0.035 equals divided by 0.045. Okay, I can't tell what's going on here. I have too many zeros here. My calculator's not set up for scientific notation here. So 1, 2, 3, 4, 5, 6, 7. So it looks like it's 2.956 and so on. I'm gonna round that last 8 to a 9 times 10 to the negative 7. Okay, And then we got to figure out how many sig figs I have here. So I got 2 sig figs here, 2 here, and 3 here. So this is going to be at 2 sig figs. Looks like 2 is my smallest number, right? So I got to round this to 2 sig figs. So this looks like this is going to go to 3.0 times 10 to the negative 7. Okay. So, but I'm looks like this is wrong. Here, 1 second here. Why is that so small? I need to check my math in this, okay? Can you see how small that is? Why would that be so small? Let me try it again. 0.105 cubed times 0.035 equals divided by 0.045 divided by 0.045. I'm not sure what I did wrong. That was really small. You see this negative 7 here? Okay, that just shouldn't be. Okay, I'm not sure what I did wrong. I apparently put something in my calculator wrong. But I see that if I put this in my calculator again, I get instead, I'm just going to go straight to the 2 sig figs because I know what that is, okay? 0.020, which is 2.0 times 10 to the minus 2. Not sure how I got that number there. But there is your answer, 2 times 10 to the negative 2. All right? Okay, so we practiced ice tables there, and we found that you can find equilibrium constant if you're simply given equilibrium concentrations of the products and reactants.